cloud colder than the leftover heat of the Big Bang. Matter heated to temperatures that existed only for an instant after creation. A dead star is so dense that atomic structure cannot survive inside it, and a region of space-time where our best equations stop producing meaningful answers entirely. These are the most extreme places in the observable universe, and every time we have found one of them, the same thing happens. What makes this worth paying attention to is not that these places are hostile. It is that they keep doing this. Every extreme we reach, in every direction, the same result. The observation comes first. The explanation struggles to follow. 4 places, 4 different ways reality becomes difficult to explain. And underneath all of them, a question that nobody has closed. Let's start with the coldest, and it is not where most people would guess. The natural assumption is that the coldest region of the universe must exist somewhere in the vast darkness between galaxies, where no star has ever burned and no energy has ever arrived. That assumption is wrong. The coldest known place in the observable universe sits roughly 5,000 light-years from Earth. It is called the Boomerang Nebula. Its temperature reaches -272 degrees Celsius, 1 degree above absolute zero. Absolute zero is the theoretical limit where thermal motion reaches its minimum possible state. A dying star at the nebula's center expels gas at roughly 160 kilometers per second. That expansion rate cools the surrounding material faster than anything in the universe can warm it, including the ambient radiation left over from the Big Bang, which holds the rest of the cosmos at a baseline of -270 degrees Celsius. The Boomerang Nebula is colder than the echo of creation itself. At temperatures this close to absolute zero, matter stops behaving predictably. Wave-like properties, normally hidden at larger scales, begin to dominate what we observe. Substances become superfluids. Electrical resistance vanishes. Quantum effects that are invisible under ordinary conditions become the governing reality. What we still cannot account for is why quantum coherence persists over scales that some models do not predict. The colder matter becomes, the more it operates according to rules our existing frameworks were not built to handle. What sharpens this into something genuinely strange is duration. The star at the nebula's center has been expelling gas for thousands of years. This is not a momentary fluctuation. It is a persistent region of space where matter has been living near the quantum edge longer than human civilization has existed. We produce near absolute zero conditions in laboratories for fractions of a second. The Boomerang Nebula has been running the same experiment for millennia, and the results are not fully consistent with what our models predict. We have been observing it since the 1990s. The explanation is still being revised. The boundary between the quantum world and the classical one we built our physics on is not a solved problem. The Boomerang Nebula sits directly on top of it. So if stripping energy from matter exposes physics we cannot fully explain, a reasonable question follows. What happens when you push temperature in the opposite direction, past anything that has existed in the universe for nearly 14 billion years? The core of the Sun sits at approximately 15 million degrees Celsius. That is the temperature required to fuse hydrogen into helium, the engine driving every star that has ever burned. In 2010, physicists at CERN briefly produced something 250,000 times hotter, a substance reaching approximately 4 trillion degrees Celsius, called quark-gluon plasma. At this temperature, protons and neutrons dissolve. The quarks and gluons composing them stop being bound together and move freely in a state of matter that last existed naturally roughly 1 microsecond after the Big Bang. The experiment succeeded. The interpretation remains unsettled. Physicists expected the plasma to behave like an extremely hot gas. It did not. It behaved like a perfect fluid, with nearly zero viscosity, flowing with an efficiency no known material approaches. More unexpectedly, some of the most successful mathematical tools used to describe aspects of its behavior emerged from techniques developed within string theory, a framework originally constructed to describe the geometry of spacetime at cosmological scales. A substance recreated for a fraction of a second in a tunnel beneath Switzerland is partially described by equations that were never designed for particle physics. That should not be the case, but it is. String theory and particle physics operate on fundamentally different assumptions about how the universe works at its smallest scales. The fact that its tools describe quark-gluon plasma accurately suggests a connection between those fields that current physics has no complete explanation for. If that connection is real and not coincidental, it would reshape how we understand the foundations of physical law. Establishing whether it is real requires a theoretical framework that does not yet exist. In the years since the experiment, physicists have continued refining their models. Each refinement has produced better predictions. None has explained why the connection works. The hottest thing we have ever created did not close a question. It opened one that cuts into the foundations of how we think reality operates, which raises something more uncomfortable. If extreme heat dissolves the structure of matter, what happens when matter is not heated but crushed? When a star between roughly 8 and 20 times the mass of our Sun exhausts its fuel, the outer layers explode outward. The core collapses inward in less than a second. What remains is a neutron star. Between 1 and 2 times the mass of our Sun, compressed into a sphere roughly 20 kilometers across. Surface gravity is approximately 200 billion times Earth's. A single teaspoon of the material carries a mass of roughly 3.6 billion metric tons. At this density, electrons and protons are forced together into neutrons. The atomic structure underlying every object you have ever encountered ceases to exist. Matter does not change phase here the way water becomes ice. It stops being matter in any form we can replicate or fully test. The object is not a mystery. Its interior still is. We can measure the rotation of neutron stars, some exceeding 700 complete revolutions per second, with precision that rivals atomic clocks. We know the surface behavior precisely. What we cannot do is confirm what is physically occurring underneath it, because the pressures at the core exceed anything achievable in any laboratory on Earth by many orders of magnitude. Competing models exist. Several remain consistent with everything we have observed. None has been ruled out. Whatever exists inside a neutron star has never existed naturally anywhere else we know of. And if that sounds like the limit of compression, it is not. There is a threshold past the neutron star where no known force can arrest the collapse further, where quantum pressure, electromagnetic repulsion, every mechanism we have identified becomes irrelevant. At that point, the question stops being about matter. It becomes a question about space itself. When a stellar remnant exceeds roughly 3 times the mass of our Sun, compression does not stop at the neutron star stage. It continues inward. General relativity, the most precisely tested gravitational theory in the history of science, predicts the matter collapses toward a point of infinite density, a singularity. Every previous extreme revealed something we could measure but struggled to explain. This one is different in a specific way. At the Boomerang Nebula, our models lose precision. At the quark-gluon plasma, our explanations become contested. At the neutron star interior, our equations disagree. At a singularity, general relativity does not become imprecise. It returns infinitely. In physics, infinity is not an answer. It is a signal that the theory has exceeded its own operating range and stopped producing usable output. The event horizon surrounding this region is not a wall. It is a restructuring of space-time geometry such that every possible direction, including directions that feel like a way, leads inward. After crossing it, the singularity is not in front of you. It is in your future, the same way tomorrow is in your future, inescapable not by force, but by the geometry of time itself. The largest known black hole, TON 618, contains a mass 66 billion times that of our Sun. Its event horizon spans roughly 260 billion kilometers across. Crossing that boundary, you would feel nothing, no surface, no warning. The universe would simply begin restructuring itself around you, quietly, without announcement. Underneath all of that sits a problem that has occupied some of the most prominent physicists alive for decades. Quantum mechanics holds that information cannot be destroyed. Every physical process is in principle reversible. A black hole appears to violate this directly. Matter falls in. The information describing that matter appears to vanish. Hawking showed that black holes slowly evaporate, but his calculations suggested the radiation carries nothing of what fell in. Where the information goes, nobody has agreed. Proposals exist. Each carries serious unresolved problems. Some require rewriting quantum mechanics. Others require rewriting our understanding of space-time. None has settled the question. At the center, our best description of gravity produces no usable answer. Around that center, one of the deepest unresolved conflicts in physics has been waiting for a resolution that has not come. That is not a gap technology will close. It is a gap in the framework itself. 4 places, 4 different ways, reality becomes difficult to explain. 4 times the same result. Cold exposes quantum behavior that outlasts our ability to explain it. Heat recreates primordial matter whose properties don't match our predictions. Density compresses matter into states our best models cannot confirm. Gravity collapses space-time toward a point our mathematics cannot describe. The most extreme places in the universe are not remarkable because they are hostile. They are remarkable because every one of them marks the same edge. Not a limit of temperature, not a limit of compression, not even a limit of space. A limit of what our current understanding of reality can describe. There is a version of physics that would account for what is happening at these locations. A framework that works where our current one goes silent. Physicists have been searching for it for decades across competing theories and contested models, and it has not arrived. We have measured these places with extraordinary precision. The closer we get to them, the less certain our explanations become. The extremes of the universe are not where knowledge ends. They are where uncertainty begins. And right now, that uncertainty is not shrinking. It is the most accurate thing we can say about the most extreme places we have ever found.